Hello. This lecture will cover pages 41 through 49 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 7A, First Order Transient RC Circuits. Starting on page 41, this chapter has to do with first and second order transient circuits. But before we start the chapter, I want to look at the overall picture. So you understand where we're going here. RC and RL circuits lead to first order linear differential equations. So a capacitor, a resistor and a capacitor, or resistor and inductor in a circuit, similar to what you have here. If you have either one of these, a resistor, series of resistors, and capacitor, or a series of resistors and inductor, it'll lead to a first order linear differential equation. Whenever you have two of these reactive elements, what I mean by two reactive elements is an inductor and a capacitor in the circuit, it leads to second order linear differential equations. We'll talk about that in the latter part of the chapter. But for now, we're just going to talk about either an RC or an RL first order circuit. So let's just take a look here. I have a first order circuit here. I have rather than an inductor and a resistor, I have a capacitor and a resistor. I have the source of EMF over here, and I have a switch. Now normally that switch is open. But at t equals 0, we're going to close that switch, and we're going to find out what characteristics of voltage and current are places on this side of the circuit. Well, the values of voltages across or current through or to a reactive element has these types of response in a first order system. It either is a charging exponential that has an equation like this, or it's a decaying exponential that has an equation like this. You might be familiar with this already, but in the time domain, this is a solution of a non-homogeneous differential equation. I don't know if you've had that in math yet, but when there's a final value, that differential equation is equal to a constant, or it's equal to a function. When that differential equation is equal to a function or a constant, it's going to have a final value with regard to time here. And you can see where that final value is up here. That's a non-homogeneous differential equation. But if your diffs are set equal to 0, you refer to that as a homogeneous differential equation. And they didn't have a final value. They had a short-term transient, if you will, but then it decayed to 0. So the only type of waveforms you're going to see in the first part of this chapter with first order differential equations is either charging exponentials that look like this, that have this mathematical form, and they come from non-homogeneous differential equations, or you're going to have discharging or decaying exponentials that have this mathematical form, and they come from homogeneous differential equations. The time constant involved in these circuits that has to do with the decay rate or the charge rate is equal to the value of resistance times capacitance in seconds. So you just find the Thevenin resistance, if you will. We'll talk more about that later. If you have more than one resistor, it's the Thevenin resistance, but as seen by the capacitor. But you take the value of R times C, and that's a time constant. In approximately 5 time constants, the RC circuit will reach a steady state or a final value. That's like a rule of thumb, and you can see that on page 44. So I'm referring back here on page 44, and you can see this table. You don't have to memorize this because it's going to be obvious here with your equations. 1 time constant, it'll reach this at the final value. 2 time constants, it'll reach this. After 5 time constants, for all practical purposes, it's reached its steady state. No, it reaching a steady state 5 time constants to this point, or it's reaching its final decay state at 5 time constants to this point. So you have to look in terms of of where you're going to be. 5 time constants where it's going to put you on the curve. You have to first decide, do you have a decaying, a rising exponential, or a charging exponential, or a decaying or a discharging exponential. I mean, 1 time constant on this form is going to put you at 63.2% of the final value, so it's going to put you up in here somewhere. That's 1 time constant. So you could basically take 0.632 times the final value, and that's where that value is going to lie. Down here, you can't do that. 1 time constant is 63% of the final value. So it's putting you down in here. So you have to multiply it times 100% minus 63.2% times this value, because you're 63.2% decayed at this point. You have to think about that. On page number 42, if you have an inductor, same thing. When you close this switch as t equals 0, we're going to look at what current does in this circuit. We're going to look at what voltage does across that inductor. It's either going to have rising exponential or decaying exponential with the same forms. The difference is the time constant. It's not R times L. It's L over R in seconds. Where you make your mistake is you think the time, it's easy, the time constant you have in a capacitive circuit is R times C. But the time constant you get in a RL circuit is L divided by R, not R divided by L. L comes first in the alphabet. So think of it that way. It's L over R. And again, approximately 5 time constants, a circuit, an RL circuit will also reach its steady state value, whether it's rising to a steady state value or it's decaying to that final value, to that 0 value. Capacitors and DC circuits. We're going to look strictly at capacitors now real quick. This is on page 43. Transient. Let's define a transient. A transient is changes in either voltage or current that happens in relatively small periods of time. After this transient phase has passed, you are said to have reached a steady state value. The capacitor has 2 transient states. You already know that. Either a charging transient, this is what it looks like, and it reaches a value. This is the transient period between 0 and 5 time constants, where the time constant is equal to R times C in seconds, and has a discharging state. There's the 2 transient states the capacitor goes through. The discharging state, it discharges. Again, there's the equation for that curve. Now, when you plot this vertical axis, all the equations you see are going to be, I'll show you the general equation is x to t. But x could take on either voltage or current, don't forget. We could be talking about voltage or current in these circuits. Here's an observation they talk about on page 263. This is really a big deal. If you see this, it's going to make all the circuits pretty easy to do no matter what I throw at you. But sometimes it's difficult for the students to see this. But let's take our time and go through this. For the RC circuit, we can assume a final solution of the variable, whether it's voltage or current, in this form. The voltage of the current is equal to K1 plus K2 e to the minus t over tau. Matter of fact, that was a solution to a first order linear differential equation that you already had in math class. If you assume that final solution, let's evaluate this at x is 0. Take t to 0. Well, if t goes to 0, the exponential goes e to the minus 0 power. And anything to the 0 power is 1. So do you see that this gets evaluated x is 0 of k1 plus k2? That's your initial condition. That's x is 0. That's when you're throwing the switch. That's when you first throw this switch at t equals 0. You're making an evaluation of either current or voltage. So in general, it's K1 plus K2. Let's just hold that thought for a minute. And at x of infinity, K1 is equal to the final value. I call it K sub F. Well, how do I get K1 is equal to the final value of x of infinity? Well, let this go to infinity right here. When t is infinity, what's he evaluated to? 0. K2 times 0 is 0, so you get x of infinity is simply equal to K1. So the final value is K1, but if you think of that and look at the equation, you already knew that. You already knew that from this equation right here, because as this is a transient, it goes away. Your final value is x, is whatever this term was, which we're calling K1 here. This is a general thought process here. Therefore, since we know what K2 is, let's evaluate K2 from this. K2 is x of 0 minus K1. Well, what's K1? Well, let's continue on here. Let's take a look at this right here. K2 is equal to x of 0 minus K1. And K2, therefore, is equal to x of 0 minus x of infinity, because we said K1 was equal to x of infinity here. So if you take a look at this right here, we know what K1 is now. Here's K1. And by substitution here, we now know what K2 is. And we can go down here and substitute these values of K1 and K2 back into that original equation up here, and we get this very important equation here. That x of t is equal to K1, and we said K1 was simply equal to the final value, x of infinity. Look at the circuit and see what the final value is going to be after all the transients died out. And then the coefficient on this decaying term, K2, is simply equal to x of 0 plus minus x of infinity. That was your K2. So on all these circuits, all you have to do is find the initial condition, find the final value, and plug it into this form here. Now, some of it's going to be real obvious, but I want you to look at that and look at that equation, and we're going to try to use that in a couple instances here. Solving for voltage or current. Here's one example. I want you to take a look at this circuit right here. I put all the variables in there, and you're going to close this switch at t equals 0. We're going to assume initial condition on this capacitor of 0. The initial condition here, V of 0 minus is equal to 0 volts. And keep in mind with a capacitor, V of 0 minus is equal to V of 0, which is equal to V of 0 plus. Remember, voltage cannot change across the capacitor instantaneously. Every time you see a capacitor in a circuit, you have to remember, when you're closing a switch, you have to remember this. V is 0 minus, V is 0, and V is 0 plus is all pretty much the same instant of time. Very close to one another. And since voltage can't change instantaneously across the capacitor, that's all true. So here I take that equation and I make my substitutions. You have to determine what the final value, VC, is. You have to find out what the initial value is, and that's this equation. You look at that circuit until you see this. Look at this circuit up here until you see that. Substitute it in there, and there's your final equation, and it looks like that. Then you can evaluate at V of 82. Once you get the equation, put 82 microseconds in here, and you can see in 82 microseconds, you can make a calculation to see you're at 31.6 volts. And compare that to how many time constants that would be. I mean, you can relate this other ways too, but I'm showing you the way to look through this using this equation. I think you could probably go straight from this circuit to that equation without doing all this. But I want you to do this until you understand it before you go from here to here. Now, how can you go from here to here? Well, you're looking at the voltage across the capacitor. You want to know the voltage across the capacitor when you throw this switch. Is it going to have a final value or not? Well, sure, it's going to have a final value because it's going to look like an open circuit at t equal infinity. So you're going to have a voltage there with respect to here. So it has to have this shape, which leads you to that form. The current in the circuit, do the same thing with the current in the circuit. The initial condition, the current in the capacitor has to be 0 because it looks like a short. Current can't change instantaneously, or I'm sorry, the current, you have to look at the circuit. Look at this circuit right here, and I want to know the current. When you first throw this switch, that current, that looks like a short there. So you can evaluate, if that looks like a short here, the current's 50 divided by 82, 8.2 k ohms. That's the current to that capacitor. It looks like a short. Well, don't forget that that current initially is going to be 6.1 milliamps. So I'm just placing these two values here in this equation for current now. Final value, initial value, final value. And I get that expression. And I evaluated 82 microseconds, I get 2.24 milliamps. You could probably see that the current's going to look like this. The current's going to be a decaying exponential in this circuit. Why? Because when you first throw this switch here, this current's going to have a fixed value based on the limit of that resistor. And why is the current capacitor going to go to 0? Because this is going to look like an open circuit at t equal infinity. When you first close this switch, it looks like a short. And then as more time goes on, it's a DC circuit. It's an open circuit. It's open. And there's no current right there. Example 2, same thing here. Except this is called a source-free circuit. That has an initial condition on it. The initial condition is 10 volts. And you're going to throw this, and what's this going to do? Well, it has to decay. There's no driving force here. There's no source of EMF. That's an initial condition on the capacitor. You throw that switch, and that decays. It's called a source-free circuit. I want you to draw both curves for the voltage across this capacitor and the current in the circuit. And here's the explanation of that. You're going to get one of these two responses. Both responses are going to look like this. The voltage is going to decay to nothing. The current's going to decay to nothing. What about solving for time? How long would it take for the capacitor to discharge to 25 volts when the switch is closed? Well, you get this form right here. You can get that equation right there, either through common sense or using this technique that I showed you over here. Once you get the expression, you have to solve for t. Given that VC of t is 25 volts. Well, I do that here, and I come down with this expression. I divide both sides by 100, and I come down with e to the minus 454.6 t is equal to 0.25. I take the ln, the natural log of both sides, which just leaves me the exponent over here. Minus 454.6 t is equal to minus 1.39. You solve for t, you get 3.05 milliseconds. You should be able to solve for t in these exponential forms. Know how to do that. You don't take the natural log of both sides at this point. That is you don't take the base 10 log. You take the natural log because that's e here. So you take the ln of this, you take the ln of that, and what you have left over here is just the exponent, and what you have over here is whatever the ln of 2.5 is. What does that turn out to be? I put too many. Yeah, it's 25 divided by 100. You get 0.25 on this side. You're taking the ln of 0.25. It give you negative 1.39. Here's example 4. And here's example 5. I worked them out in detail for you. Make sure you understand how to do those. And that concludes this lecture.